Hello and welcome to lesson 34. We're looking at higher derivatives today. So what's the goal? I want you to understand what a higher derivative is and its notation. And then can you actually apply the rules to differentiate different equations? So we're still using our power rule, product rule, quotient rule, chain rule, implicit differentiation. We're just going through and doing it for higher derivatives. Now what do higher derivatives mean? It simply means, in terms of ours, or what we're working on here, it just means a derivative beyond the first. So if we're talking about it in function notation, we would have the function f of x, we would have its first derivative, and now what we're looking at is dealing with the second derivative, dealing with the third derivative, dealing with the fourth derivative, and I've seen textbooks go both directions here. Instead of using the four strokes, they go to Roman numerals, and so on and so forth. Standard notation. Standard notation, again, you start with a y equals, y prime, y double prime, y triple prime, and y quadruple prime, and so on and so forth. And then we have Leibniz, where he said y equals dy by dx equals di squared y by dx squared, di cubed y by dx cubed, and so on and so forth. So the exponent goes on the d on the top and the x in the bottom. So there are your notations that we're going to be dealing with. All right, so just some examples. Determine the second and third derivative of that function, and it's in function notation. So I'm going to continue with the function notation. So we want to know second and third. And the only way you can get there is by doing your first derivative, negative 28x cubed plus 15x squared. So there's your first derivative. Second derivative, you do the 28 times 3, so we get negative 84x squared plus 30x. And the third derivative, f triple prime, is equal to negative 168x plus 30. So the answer is our last two lines. That's all there is to it. So you're sitting there watching the video thinking, what's the catch? The catch is when you get into different types of functions. When you get into quotient rule, when you get into implicit, that's the catch. So there is one. So you were right to expect something to come along, but what you're going to find is it's more of an algebraic challenge. The actual derivative doesn't really get that much harder. So here we have a quotient rule, so I'm just going to apply the quotient rule. And it says determine the second derivative. And usually, if I'm in a good mood and you've been nice to me, I don't usually go quotient rule beyond second derivative because it does tend to get, or can get ugly. So keep that in mind. Stay on my good side. Derivative of the top function multiplied by the bottom minus top function multiplied by derivative of bottom. Losing control of my brackets here, just one sec. Top function multiplied by derivative of bottom, all divided by the bottom squared. So here's an example where you do have to clean it up. So I do get to see some algebra skills. So I'm going to distribute, collect like terms before I move on to the next derivative. You always want to do that. So we end up with x squared minus 4x over the x minus 2 squared. If I took out I can take out an x, it's a common factor on top, but what we find is really there's nothing to cancel out on the bottom. And I much prefer it to stay like this so I don't have a product rule on the top. So second derivative. Derivative of the top, 2x minus 4, multiplied by the bottom function, minus the top function. And now you have to take the derivative of the bottom function. That bottom function is now a power outside those brackets, so we have to use the chain rule. So that means we'd have the 2 multiplied down, x minus 2, and I'll put the exponent 1 in for good measure, multiplied by the derivative of what's inside, which is just a 1, and the denominator gets squared, so x minus 2 would now become to the 4th. And there you go. Again, keep in mind, I'm just marking process, so you're not going to have to simplify this last step here for me. You're going to leave it in that format right there. All right. If you go ahead and do some simplification, I'm not going to stop you, of course, or dock you marks, but keep in mind you're wasting valuable time here. Okay, second one. It's implicit differentiation. Is there anything difficult here? Power rule, power rule, power rule. So you must be in a good mood today. So derivative of 2y is going to be 2 times 1, because that's derivative of y prime, minus y squared would be 2y to exponent 1, and that's where that notation gets kind of funny. You got to be careful, so I'm just going to go 2y, y prime equals 4. So it's going to be easier, right now it's easier to get y prime by itself. I'm going to factor it out. So y prime equals 2 minus 2y, that's equal to 4. And I'm going to get y prime by itself now that I've gone the distance, 2 minus 2y. Now I'm going to take the derivative of that. So now I'm going to quotient rule. So if you rearrange your implicit differentiation into the y prime equals, then you don't have to use implicit again. So y double prime, derivative of the numerator, the derivative of the top function, which is a constant, 2 minus 2y minus top function multiplied by derivative of the denominator over the denominator squared. Okay. And this actually simplifies down pretty nice. I'll just do it here for argument's sake. That's going to go to 0. So you end up with 8 over 2 minus 2y all squared. All right, so that second derivative doesn't look that nasty. Previous one would take a little bit of work to simplify, but you also find it would go down to a polynomial over polynomial. All right. And I guess what I could show you, if we go back for a sec, for argument's sake, if you do have to take, I'm talking about this one, so let's go back one sec here. If you do have to take the derivative of this one, or you need to simplify it, what you'll notice, and I'll show you here while I'm thinking about it, if you look at those, there's really 2 terms on top. We have a common factor on top, and that's that x minus 2. So we could take an x minus 2 out of both terms before doing any simplification, which would reduce it to a 2x minus 4, multiplying an x minus 2. So now you just have a binomial times a binomial, minus x squared minus 4x multiplied by 2, because that x minus 2 came out, and then the x minus 2 to the 4th. And you get a bit of cancellation. That term would reduce that exponent to cubed. And then if you look inside here, okay, there's really, it's just binomial times a binomial, so it's not nearly as nasty as you initially thought. So usually there is quite a bit of factoring involved. It works out that you can factor. All right, I think this is the last example. Yep, find all derivatives. So all derivatives means we got to take this down to 0. So h of x would equal to 5x cubed minus 4x squared plus 7x minus 3. So basically it is keep taking derivatives until h of whatever prime is equal to 0. First derivative is 15x squared minus 8x plus 7. Second derivative is 30x minus 8. Third derivative is 30. And my fourth derivative is 0. So there are all of your derivatives for this function. Now, I will point out, and some of you might be thinking, how often do I have to do this? This only works for polynomials. Okay? Can only find all derivatives for polynomials. Okay, because if we look back here at a previous example, with the implicit, it's going to keep going. Even though there's a constant on top, there's still a derivative on the bottom. If you look at the g of x function here, this one, you'll never ever get it down to 0 because there's always variables, there's always material on top. So it only works for polynomial functions. So that's kind of nice. So you know it's not going to be the end of the world if you're asked to do that. So just trying to bring that homework up a little bit. So there's the assigned homework for this video. If you have any questions, make sure you ask next day. Good luck.